this video, we'll learn about methods to analyze frequency counts in a contingency table, also called two-way frequency table, a table that consists of frequency counts of categorical data corresponding to two different variables. One of the definitions of contingency is dependency. We use the term contingency because we test for independence between row and column variables. In a test of independence, we test the null hypothesis that in the contingency table, the row and column variables are independent. Basically, that there are no dependency between row variable and column variable.
Let's take a look at the following example that is presented as a contingency table with 4 rows and 2 columns. The row variable identifies the treatment used for stress fracture in a foot bone, and the column variable identifies the effectiveness of the outcome as success or failure. We're going to test the claim that success of the treatment is independent of the type of the treatment. And after we have the results, we'll be able to answer the question, what does the result indicate about the increasing trend to use surgery? First, we need to check if the requirements are met. First requirement, the sample data are randomly selected. Considering the source of the study, the table is based on data from Surgery Unfounded for Tarsal Navicular Stress Fracture by Bruce Jensine, Internal Medicine News, Volume 42, Number 14. We will treat the subjects as being randomly selected and randomly assigned to the different treatment groups. So the first requirement is met. The second requirement is that the sample data must be represented as frequency counts in a two-way table. It's called two-way table because it has two variables. In this case, we have two variables, treatment and the effectiveness of the procedure, and the results are represented as frequency counts, not as a mean or other statistic. In this case, we have 54 subjects who had success with surgery treatment and 12 subjects who had failure results with the surgery treatment. 41 subjects who had success with weight-bearing cast treatment, and 51 subjects who had failure with the weight-bearing cast, and so on. So the table represents frequency counts. And the third requirement, for every cell in the contingency table, the expected frequency E is at least 5. The formula to find the expected frequency is kind of complicated. It involves several steps. First, we need to find the row total, multiply by the column total, then divide by the grand total for each cell. So let me show you how to do it in Excel. I copy the data from my document to Excel. Let's create another copy. These are observed frequencies. We're going to create another table to calculate expected frequencies. I'm going to clear the cells. The expected frequency for the success category in the surgery treatment will be found by multiplying the row total by the column total divided by the grand total. So let's find the total for each category. Let's create the formula to find the totals of all rows and the columns. Equal to sum, open parenthesis, select the values you want to include in the total, close parenthesis, enter. And then we're just going to grab this cell and extend it to the other 3 columns. We'll find the total for the columns the same way. Equal sum of, open parenthesis, select the cells, close parenthesis, enter. And we're going to copy this formula to the next column as well. Now let's find the grand total. Equal sum, open parenthesis, select the sum of all rows, close parenthesis, enter. 253 is the grand total. Now let's write the formula to find the expected frequency for each category. For the first category, surgery, in success equal 66, the row total, times 182, the column total, divided by 253, the grand total, equal 47. surgery failure is equal row total 66 times column total 71 divided by 253, the grand total. Enter. Let's continue with the rest of the data. If you're getting something like this, the numbers to several decimal places, and you want to decrease the number of decimal places or increase, you can always use decrease decimal places or increase decimal places icons. I'm going to leave it to 3 decimal places. We did these long calculations just to make sure that each cell's expected frequency is at least 5. The smaller expected frequency is 6.174, so all 3 requirements are met. We can interpret the expected value by stating that if we assume that success is independent of the treatment, then we would expect to find that 47.478 of the subjects would be treated with surgery and that treatment would be successful. There is a disparity between observed frequency 54 and expected frequency 47.478. So let's conduct a hypothesis test to see if the effectiveness of the procedure independent on the treatment or dependent. So our original claim is that success of the treatment is independent of the type of treatment. Opposite claim would be that success of the procedure depends on the treatment. Null hypothesis in a test for independence is that success is independent of the treatment. An alternative hypothesis is that success and the treatment are dependent. We are going to use significance level alpha of 0.05 and we'll perform the hypothesis test for independence in StatCrunch. Let's copy the data from our file to StatCrunch. The first column represents treatment, second column success, third column failure. To do the test for independence in StatCrunch, go to Stat, Tables, because we are working with the table, Contingency, with Summary. We don't have raw data, we're working with summary statistic with frequencies. Select columns, success and failure. Variable will be in column treatment. Compute. Let's write down the p-value. P-value is very, very small, less than 0.0001. It is smaller than alpha of 0.05. Therefore, we reject the null hypothesis of independence between success and treatment. It appears that success does depend on the treatment. Although the results do not tell which treatment is best, we can compare the success rates. The success rate in the surgery category is 54 divided by the total, 66 times 100 to convert it to percent, is equal 81.8%. Success in the weight-bearing cast category is 41 divided by 92. The total in the weight-bearing cast category times 100 to convert it to percent is equal to 44.6%. The success rate in non-weight-bearing cast for 6 weeks is 70 divided by 73 times 100, 85.9%. And the last category, non-weight-bearing cast for less than 6 weeks, 17 divided by 22 times 100 is equal 77.3%. The success rates suggest that the best treatment is to use non-weight-bearing cast for 6 weeks. It has 95.9% success rate. Now let's go back to the second part of our question. What does the result indicate about the increasing trend to use surgery? Well, the results suggest that the increasing use of surgery is a treatment strategy that is not supported by the evidence. Because we could see from the calculations that the best treatment for a stress fracture in the foot bone is non-weight-bearing cast for 6 weeks. Now let's use the critical value method. The chi-square test statistic is equal 58.393, and we need to find critical value to compare the test statistic with. Critical value is the value that separates critical region from non-critical region. To find critical value for the chi-square, go to Stat, Calculators, chi-square. Degrees of freedom is found by using the formula R minus 1, the number of rows minus 1, times the number of columns minus 1. We have 4 rows, 4 minus 1, times 2 columns, 2 minus 1, 3 times 1 is equal 3. So degrees of freedom is 3. Change the direction to the right. The area to the right is 0.05. Compute. The critical value is 7.815. Because the test statistic is in the critical region, 58.393 is significantly higher than the critical value of 7.815. It's going to be way on the right side. The conclusion is going to be the same. We reject the null hypothesis of independence between success and treatment.
I hope that was helpful. For more videos, check my playlist, JB ABC Statistics. I will see you soon.